Welcome to the 13th lecture of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. Myself Mukul Kumar Das from Department of Electronics Engineering, IIT ISM Dhanbad. In this lecture, we will mainly focus light matter interaction and solar radiation. In the last class, we have discussed some metal insulator semiconductor junction and MIS solar cell. Also the carrier transport mechanism in MIS solar cell. And in this class, we will focus on light matter interaction, which is very important in context of this course, that is solar cell modeling. Then absorption characteristics of semiconductor material, wavelength dependencies of absorption coefficient, solar radiation spectrum. These are all important in context of the modeling of solar photovoltaic cell. Say light matter interaction. Until the 1905, people were believing that light is a wave, electromagnetic wave. And Young's double slit experiment, which is very famous experiment, it was clearly explained by the help of the concept that light is an electromagnetic wave. But in 1905, Einstein, the renowned scientist, invented photoelectric effect. That means on incident of light of suitable wavelength on a material, it can eject some electrons. This is the basis of the photoelectric effect. And if light is a wave, how it can interact with the electron? How it can escape the electrons from metal or any material surface? So then the concept of particle nature of light came into the picture. And this effect, the photoelectric effect, could not be explained without the concept that light is a particle. So ultimately, the particle theory of light is established. And what is the particle theory? Particle theory means light is nothing but it consists of tiny packets of energy called photons. And each photon behaves like a particle, carrying specific amount of energy that depends on its frequency. And frequency again means it is a wave property, that is a frequency or wavelength. So that means in this way the particle and the wave, both natures are related. So finally we can consider that light is nothing but a particle, which is nothing but a tiny packets of energy or photon. This is called photon, and this photon behaves like a particle carrying a specific amount of energy, h nu. H is Planck's constant and nu is its frequency. But remember, the photon has no mass, no charge, but it carries energy and momentum. That is a peculiar thing. So it carries energy and hence momentum, because energy and momentum through the wave nature is related by some relationships that we have seen in case of electron also. But it has no mass and no charge. So this is the final conclusion of the particle theory, that photon is a quanta, that is the smallest discrete unit of electromagnetic radiation. Is the smallest discrete unit of electromagnetic radiation. It has no mass, no charge, but it carries energy and momentum. The energy of a photon is h nu, where h is Planck's constant and nu is a frequency. Nu is the frequency. Now, how light is absorbed by a semiconductor material, that is mainly important for our device modeling, that is solar cell modeling. Light absorption and electron hole pair generation. So let us see the mechanism of carrier generation in a semiconductor on incident of light, or it is called photogeneration. When a photon with energy, say E photon is h nu, suppose, strikes a semiconductor, and if the energy of a photon is greater than or equal to the band gap of the semiconductor material, the photon can excite an electron from valence band to the conduction band. That means, suppose we have a semiconductor, and if we draw the band diagram, this is a valence band, this is a conduction band minima, and this is a valence band maxima. So when light is incident, so h nu energy per photon is coming, and this h nu energy may be transferred to the electron in the valence band. And if this electron gets energy with the interaction of this photon, its energy becomes high, and if this energy h nu is greater or at least equal to the band gap of energy, this band gap energy Eg, then this electron may transit from here to here, leaving behind some holes here. So here it leaves behind a hole, and this electron is coming here. So this electron, when it reaches to the conduction band, it is free. This hole in the valence band is also free. So that is a pair of electron and hole is generated. So this is the mechanism of electron hole pair generation. But many other insights, important insights related to this matter are there. This transition will occur only if the energy of h nu greater than band gap energy. Otherwise, it will not absorb. Suppose we have a semiconductor bar. And this semiconductor bar is illuminated by a monochromatic light. Monochromatic light, why I am mentioning? Monochromatic means single frequency or single wavelength. It is illuminated, so light is, say, incident from left side. And say the photon energy of the light which is incident, that is h nu. And here we have considered monochromatic, that means nu is single valued. That means the light incident is of single frequency or single wavelength. The intensity of the light, what is the incident in this front surface, it will gradually decreases due to absorption of light, because the intensity, which depends on the number of photons incident. So out of the total number of photons, if some number of photons are getting absorbed, automatically the number of photons in the beam, in the light beam, will be reduced. So if we consider the intensity at the incident plane is I0, intensity of light, and the transmitted intensity, say IT, transmitted, and this is I0, they are related by a relationship IT is equal to I0 e to the power minus alpha into D. Now what is D? D is nothing but the thickness of the semiconductor bar. What is alpha? Alpha is absorption coefficient of material, which is very important. And alpha, its unit is either centimeter inverse or meter inverse. Alpha high stands for the rate of decrement of intensity will be more. There is more and more light will be absorbed. So alpha is nothing but a material property. So every material cannot behave in a same manner. Alpha will be different. Not only alpha is dependent on material, for a particular material also, alpha depends on wavelength of light. So same material, if it has a alpha value, say 10 to the power 4 centimeter inverse, for blue light, for the same material, this alpha value may be 10 to the power 5 centimeter inverse for red light. Now how this is related to the material parameter alpha? We know the refractive index of a material is very known parameter, very well established parameter called refractive index. It is nothing but the ratio of speed of light in air and speed of light within the material. So refractive index basically a complex function, and this refractive index itself is a function of wavelength, and as the refractive index is a complex, it has a real part and imaginary part. So let us see n is equal to n real plus j k. K is the imaginary part. And this is the real part. The real part is responsible for changing the phase of the light when it is propagating through a material or media. But the imaginary part, K, that is responsible for absorption. And alpha is nothing but 4 pi, this imaginary part K, by lambda. So this K itself is a function of wavelength, and again another lambda term is there. So alpha is a function of wavelength. So this is the physical significance or relation of alpha, absorption coefficient of a material. So ultimately we got that alpha is a wavelength dependent function. For the same material, if the light wavelength changes, its absorption coefficient will change. We know glass is transparent, but silicon is looking like black. Why? So we have discussed that nu must be greater than critical frequency for absorption. Similarly, lambda must be less than lambda c for absorption. Glass is transparent, whereas silicon is black. Because glass has band gap in the order of 8 electron volts, say, very high band gap. High band gap means it needs very high energy to be absorbed, but the visible range wavelength, if you see, that is in the range of say say 400 to 700, 800, 750, 700 in this range. So corresponding to that wavelength, the energy is not sufficient to overcome or to become greater than 8 electron volt. That's why most of the means all wavelengths, all light in the visible wavelength, visible range wavelength will be passing through the glass. So it looks like a transparent. But in case of silicon, its band gap is 1.12 electron volt, and if you calculate the energy corresponding to this 1.12 electron volt, you can see the light in the visible range will be absorbed by the silicon, not transmitting through the material. That means silicon looks like a black or gray color. So this is a daily life experiment also. So by looking the color, you can predict the band gap in this way. Anyway, so we have told that wavelength should be less than critical wavelength and frequency should be greater than critical frequency for absorption. So we can have an idea about the nature of alpha, absorption coefficient. So it must be wavelength dependent, because up to certain wavelength it is absorbed, and beyond which it will not absorb, because lambda must be less than equal to lambda c, or in terms of frequency it is reverse. So if we have a concept like that, the nature of alpha, that is absorption coefficient, which is 4 pi k by lambda, so k is a function of lambda also, ultimately, so this type of nature you can expect. So suppose there is a sharp change, then suppose site. That means below this region, below this lambda c, wavelength will be absorbed, and above this is very slight. It should be ideally 0, but due to some defects in the band gap, in the forbidden gap. So there are some absorptions. Anyway, so value is very less. So this is called tail in the absorption. So this type of nature we can predict for the absorption coefficient alpha. If we observe the absorption coefficient for different semiconductor materials, and several papers and materials have already reported regarding the values of this alpha for different materials, it looks like that. Exactly the conceptual figure, whatever I have drawn, it looks like this. You see, this is the nature of alpha for different materials. Say silicon, here it is silicon. You see this dash line, this is silicon. You have a sharp decrement at a particular cutoff wavelength. All the things are there. So below this wavelength, the nature of the alpha, that will vary material to material, and that will depend on some other parameters, other effects or other factors. But the nature that there is a very sharp decrement at this lambda c, that is valid, that is being followed for all the graphs. So there are two graphs drawn, one for solid line, another for dash line. Solid line stands for room temperature and dash line at 77 K. That means the absorption coefficient depends on temperature also. Not only absorption coefficient value, the cutoff wavelength also, because we have shown the band gap of a semiconductor material depends on temperature, band gap variation. So you see 300K for silicon in the same, this is the solid line for silicon, and this is the solid line for silicon, and this is the dash line for silicon. So that means this is the 300K plot and this is 77K plot. You see for 300K lambda cutoff, lambda c is more than this value, and this is consistent with the variation of band gap. With increasing band gap, with increasing temperature, band gap decreases. That means band gap decreases means nu C will be increasing. Nu C will be increasing means so value of nu greater than nu C will be absorbed. So lambda less than lambda C will be absorbed. So lambda C, that will be more in this case of 300K. Anyway, so the nature, conceptual nature relates with the conceptual behavior. Absorption coefficient depends on other factors, say temperature. So here graphs are shown for two temperatures, on 300K, that is room temperature, another is 77K, and this is for silicon solid line and silicon dash line. Dash line stands for at lower temperature and solid line at room temperature. You see the lambda c at higher temperature is more than lambda c at lower temperature in this case. So not only the value, the cutoff wavelength also affected by temperature. In this way alpha can be obtained, and if we know the alpha value, we can calculate the absorption coefficient of we can calculate the intensity at the output of the semiconductor material when light is passing through the material. Now the case is important when h nu greater than E greater than h nu. I have considered in the last figure that energy of the photon is equal to h nu, and that energy is transferred to the electron in the valence band, and that will be migrated to the conduction band, leaving behind a hole. In this way, electron hole pairs are generated. But consider the case energy of the photon greater than the band gap energy. What will happen in that case? Say this is conduction band minima, this is valence band maxima. Suppose this is conduction band minima and this is valence band maxima. H nu greater than Eg. That means say this is Eg and h nu is equal to say E1. E1 is this value. E1 greater than Eg. So electron in a state here, it may transit to the state in the conduction band here, but within a moment, very quickly, this electron will come down to the conduction band minima through lattice scattering, due to lattice scattering, or through transfer of heat to the lattice, because from here to here transition occurs that produces an electron which has a high kinetic energy, and this kinetic energy will be transferred to the lattice. And in a semiconductor lattice, you know, lattice is always vibrating due to the vibration of all the atoms, and it is a effect of togetherness. So if individual atoms vibrate, so as a whole lattice vibrates. So combination of all vibration of atoms creates a lattice vibration, and this lattice vibration will be more if the energy of this high energy electron are transferred to the lattice vibration, transferred to the atoms, and after releasing this extra energy, it comes down to the minimum of the conduction band. Similarly, hole, it may release energy and to reach here, and this electron may further recombine to the hole in the valence band maxima. Not necessarily the hole which is coming after releasing energy which is coming here, that this electron will recombine to that. It may be different, but there will be recombination. So this process from valence band to conduction band transition is called absorption, and this process from conduction band to valence band, this is called radiation or emission, and this also called recombination. Basically, electron recombines with the holes in this process, and in between there is a process. This is due to lattice scattering. Energy is transferred to lattice vibration. This is a short time phenomena. This is short time. And the time is why important? Because the generated electron hole pair due to incidence of light must be separated out in a solar cell before their recombination. That means, suppose at t is equal to 0, this transition occurs, and t0 plus delta t, this occurs. After this, it takes suppose delta t dash time to recombine with another holes. So delta t plus delta t dash, these two time is important, because if we can separate these electrons and these holes in a opposite side before this time delta t plus delta t dash, it can produce a voltage at the terminal. So in this context, the time is important. So there is a continuous process of this type of generation and recombination if light is incident on a material, particularly if light incident with energy greater than band gap energy. And in this process, some energy is lost. Lost means some of energy is lost to the lattice vibration. It increases lattice vibration. So this lattice vibration means heat. So energy can be also expressed in terms of heat energy. So lattice temperature will be increased in this process. We will show how the time is important, how they are related to the rate of generation of electron hole pairs at steady state. Now suppose you have a semiconductor bar with incident energy say P0, incident power. Energy means power is joule per second or watt, and the transmitted energy is PT, is watt. If say incident power P0 and this PT, so PT, the transmitted power, that will be P0 e to the power minus alpha d, that I have already discussed. Say the incident power and the wavelength of incident light in such a way that, so this h nu value say 1.6 electron volt, that is E1. Say E1 is 1.6 electron volt, and suppose Eg is 1.4 electron volt. So we can calculate the power transferred to the heat. How? Suppose the incident power is P0 is equal to say 15 milliwatt, and say P out or PT, that is equal to say P out is equal to say 9 milliwatt. So how much power it is absorbed? So absorbed power will be P0 minus say P out 6 milliwatt. Out of this absorbed power, some power is transferred to the heat and some we can get back in the form of say light again. So this H nu suppose in the order of 1.4 electron volt. So that corresponds to the H nu will be corresponds to the 1.4 electron volt. So rest of the power is transferred to the heat energy. So this 6 milliwatt, this power, so what is the fraction of power converted to heat? That also can be calculated. So this is the absorbed power. Out of this absorbed power, some fraction of this power is converted to the heat and some is in the form of H nu. Also you can calculate from the calculation though how many number of photons are incident, because if it is 15 watt say P0, that is joule per second, that is per second, this joule amount of 15 joule is incident. So number of photons means single photon has energy H nu. So H nu, if we express in electron volt, 1.6 electron volt, so that should be fast converted to the joule. So H nu is equal to say 1.6 electron volt. So that indicates into 1.6 into 10 to the power minus 19 coulomb. Electron volt, electron is this coulomb into volt, so this is basically joule. So number of photon incident per second, that will be 15 into 10 to the power minus 3, because this is milliwatt. So this watt by 1.6 into 1.6 into 10 to the power minus 19. In numerator this is joule per second and in denominator it is joule. So ultimately this is number per second. This is number per second. So this amount of photon is incident. So what is the number of photons coming out? If we consider so efficiency, quantum efficiency, perfect quantum efficiency. Perfect quantum efficiency means each recombination of electron hole pair gives radiation or photon. So if there are 10 number of recombinations, 10 photons will be coming out. Generally, out of 10 recombination, 10 photons are not coming out. Some photons are, some recombination radiates some heat energy also. So in that case it will be non 100%. But if we consider this a perfect conversion efficiency from recombination to photon, then we can calculate the number of photons emitted also from the output power. And this, in that case, we have to calculate and we have to consider 1.4 electron volt of energy. Be careful, not 1.6 electron volt. So the absorbed power, what is the 6 milliwatt? First we have to determine out of this 6 milliwatt how much power is converted to heat and rest of the power will be giving the photon at the output if there is a 100% efficiency. This can be calculated in a same way. So detailed calculation of this type 1 problem will be discussed in the tutorial section of this week. But in this way, we like to mention that if the h nu greater than band gap, so some energy will be lost. So generally, in case of solar cell, high energy, that is very low wavelength, that is blue region. Particularly for silicon solar cell, the blue region of light will have higher energy, and in that case transition of electrons from deep to the into the valence band to the state above the conduction band minima occurs, and in that case this amount of energy is transferred to the lattice. So lattice temperature is increased, that will be a loss. So that encounter loss is called blue loss. Several other techniques are also, people are trying to utilize this lost energy to convert it into the ultimately photovoltage, so that we can reduce the loss and enhance, ultimately we can enhance the efficiency. Anyway, that will be discussed in detail in the modeling section of solar cell. One thing again I want to mention here as a thumb rule, you can remember the calculation of this critical wavelength and critical frequency can be calculated in this way, because this, if you calculate, it takes huge calculation, because h nu Eg is equal to h nu, that is nothing but h c by lambda. So by putting the value of h, that is 6.62 into 10 to the power minus 34 joule per Kelvin, and this c is velocity of light, speed of light in free space. In this way you have to, it is a cumbersome. So but the thumb rule tells that lambda in micron can be obtained as 1.24 by Eg in electron volt, a very well known formula for calculating the critical wavelength if band gap is given, or if wavelength is given, band gap, which is the minimum band gap required for that, can be calculated. But be careful, this Eg in electron volt and lambda will be coming in micron. Ultimately, whatever we have seen, alpha depends on wavelength. Also, the h nu, energy of a single photon, if it is more than band gap, so there are some losses. In context of solar cell, as it is illuminated by our solar radiation, we need to have a knowledge on the solar radiation and how it varies with wavelength. This is called solar radiation spectrum. In solar radiation, air mass, one term is very important. What is air mass? So air mass basically is a measure of the path length of sunlight crossing through the Earth's atmosphere. That is how much length light is crossing before reaching to the Earth's surface from the sun. So this is the measure of air mass. Is a measure of the path length of sunlight crossing through Earth's atmosphere. Means the length, amount of the length which is crossed by sunlight through the atmosphere. This, suppose this is the atmosphere, this is the Earth's surface. You see, this is the Earth's surface. If this is the Earth's surface and this is the atmosphere, So this length, length of atmosphere crossed by sunlight is called air mass. And this length actually depends on the angle between sun and the particle, of course, because if you are calculating the here, so the sunlight is coming from this path, in following this path, so it crosses this length. So for in other case it will be have a other lengths. So ultimately the position, so whether sun is exactly on the in the normal position or not, that depends the length of the atmosphere which the sunlight crosses. So there are different standards. So AM0 standard, it represents the solar spectrum in outer space before it passed through the Earth's atmosphere. Actually, in Earth's atmosphere, there are scattering, there are absorption of sunlight. That's why to account these things, we have to calculate, we have to maintain some standards, we have to make some standards that we have made. And this AM0 means before Earth's atmosphere here. So this is AM0. So here radiation will be much higher than the radiation here, because some radiation loss due to this atmosphere on the Earth surface is there. So AM0 is this. AM1 is like this. So this is direct, but it is on the Earth surface. AM1.5, it represents the solar spectrum on Earth surface when the zenith angle is 48.2. Suppose this is the position of sun, and here, and this angle between this normal and this position, if it is 48.2 degree, in that case the radiation reaches at this surface after crossing the atmospheric length, it is 1.5, AM1.5. Similarly, for other position, if this angle is 60.1 degree, this will be air mass 2. So based on the position on the Earth surface, that is the location. So in case of India, mainly we are around the equatorial region. So in that case, it will be different from other countries, say Europe countries and other things. They are not at the near the equatorial, so they have a less radiation generally. So this radiation difference is standardized by different numbers, AM number, air mass number. And out of 1.5 G, again, there are two matters. One is global, means this spectrum includes both direct sunlight and diffuse sunlight. Actually, from our sun to the Earth surface, when sunlight reaches, so direct path, in this direct path, there is a loss, after loss it reaches here. But also some radiation intensity added due to diffuse of light. So during this path, so some other, it follows some other paths due to scattering, diffuse, etc. Diffused by some particles in the atmosphere. So ultimately, some radiation may be increased, may be decreased, depending on the total value. So this is called AM 1.5 G total. So this is global, means this total. So it includes both the direct sunlight and diffuse sunlight scattered by particles in the atmosphere. And 1.5 D, that is direct, this spectrum represents only the direct sunlight from sun's disk without diffuse light. But mostly AM 1.5 G is suitable for calculation, because obviously to reach the light on a Earth surface, so light may come directly, some portion may come directly, and some due to scattering by the particles in the atmosphere. So total radiation, how much it is reaching on the Earth surface, that should be taken in calculation of parameters of the solar cell. So these are the standards of this solar radiation. So solar radiation standards are very important. AM0 here, AM1 here, when sun is on the top exactly, that is vertically on the top, that is a normal position, and outside the atmosphere, AM 1.5, this when this is an angle 48.2 degree, the radiation reaches here is called 1.5. Out of this 1.5, two cases are there. And if this is 60.1 degree, that is AM2. If it is more than that, AM more than 2 also there. So generally in India we always take AM 1.5 G for simulation of solar cell and other things, other parameters. Now the solar radiation spectrum, which is also important, the wavelength dependent solar radiation. So how it is depending on wavelength? Because we have seen the wavelength of incident light is very important concerning the absorption of that light by a material. If you choose a material, say band gap particular value, say 1.12 electron volt, so up to a range of wavelength it will absorb, beyond which it is not absorbed, and that is governed by the relationship that critical wavelength lambda c in micron is equal to 1.24 divided by band gap in electron volt. So to know the radiation spectrum is important. So this is the very typical solar radiation spectrum. It starts from the wavelength very low value, so like 250, and it ends up to 2500 nanometer. But this is the visible range, you see. So nearly 400, and this is the 750 near about, this is called visible. Then it is infrared region. There also some radiation comes, and out of this infrared there is a long wavelength infrared, short wavelength infrared. These are the regions are defined in infrared region. And below the visible, in wavelength scale, below. In energy scale it is above, in wavelength scale it is below the visible. This is UV, ultraviolet. So this is the spectral irradiance. Spectral irradiance is plotted along y-axis, and this is nothing but watt per meter square per nanometer. This nanometer indicates the wavelength, that is per area at a particular wavelength per nanometer, small gap of wavelength in nanometer, this amount of wattage is coming. So this is the meaning of irradiance. Be careful about the unit. Whenever we will be using this to calculate the solar cell parameters in the simulation, so this unit should be taken care of very carefully. The watt per meter square per nanometer, and this is the wavelength axis. And AM 1.5 global, AM 1.5 direct, AM0. AM0 is taken for reference value actually. Generally we take AM 1.5. If we see the wavelength dependent spectrum of AM 1.5G standards solar radiation, it is indicated by blue line. This is the blue things are there, and AM 1.5 direct is green. So direct is less than total, of course, because direct means you are not considering any light which is reaching by a non-direct path, that is indirect path by scattering of material particles in the atmosphere. So that is generally direct is less than global. Global considers both direct incident path, light coming to the direct path, also coming through the scattering of materials in the atmosphere in the indirect path. So this is generally higher, and 0 obviously much higher, because 0 stands for outside the atmosphere. So sunlight will be much more, radiation, irradiance will be much more. So this is the wavelength versus plot. So these are the important thing we have to use later for calculation or for simulation of solar cells. So ultimately in this class we have discussed light matter interaction and dual nature of light, particle as well as wave nature. We have discussed generation of electron hole pair in a illuminated semiconductor. We have discussed both the cases or all the cases. If h nu less than band gap, it is transmitted through the material. If h nu is equal to band gap, electron hole pairs are generated, and electron hole pairs are generated with not an extra kinetic energy, that is from valence band maxima to conduction band minima. But if h nu greater than band gap, then transition of electron from a state inside the valence band to a state inside the conduction band occurs, and it creates some losses because some extra kinetic energy of the generated electron and hole will transfer to the lattice, and lattice temperature will increase. In that case, that will be a loss of incident photon. Air mass, different standards have been discussed, and its significance also discussed. And finally, solar radiation spectrum we have discussed, that is depending on wavelength. This will be used for calculation of solar cell parameters in later classes. The references, these are the books already we have referred earlier, and this is the some data from the PV education. This link we have taken, you can also take. Thank you.